Imagine you are pushing a critical hotfix. It's late on a Friday.
Oh, it is always a Friday.
Right. Always. And the production database is just throwing errors. The company is actively losing money by the minute, and you have finally found the culprit. It's a tiny logical error in a back-end module.
Usually just one line of code.
Exactly.
Yeah.
So you fix it, the code works, you hit deploy, and your workspace build tool just stops you cold.
It just throws a wall right in front of you.
Right. It looks at your hotfix, notices that you didn't update the corresponding structural tests to match, and literally throws an error flag in your terminal. So you try to force it through, looking for that bypass command.
The panic sets in. You're looking for -- force.
Yeah, you find a flag, but it's not -- force. It's literally titled -- you will be fired.
Which is just, it's the ultimate line in the sand. It tells you exactly where the system's priorities lie.
Welcome to the deep dive. If you are listening to this right now and thinking about your own team's messy GitHub repository or, just the sheer anxiety of pushing a hotfix to a sprawling monorepo, you are going to want to hear this.
Oh, absolutely.
Today, we're looking at the source material for a tool called A, specifically the @A01/A0 package. And our mission today is to really unpack how A operates as this radical, ultra-strict workspace scheduler.
It is a complete paradigm shift.
It really is. It completely abandons the heavy daemon background processes and the massive plugin bloat you usually see in traditional tools like Next. Instead, it prioritizes absolute, uncompromising workspace truth.
Workspace truth. That's the core of it.
Right. Okay, so let's unpack this. Imagine you as a fitness coach who completely refuses to count your reps if your form is even slightly off.
I've had coaches like that. It's frustrating.
Oh yeah, you try to push through, you do a sloppy push-up just to get the numbers on the board because you're exhausted, and the coach just stares at you, writes down failure in pen, and makes you start over.
No half reps allowed.
None. That is A0 for your code base.
And to understand why it acts like that fitness coach, we really have to look at the fundamental contract between a developer and their workspace.
What do you mean by that contract?
Well, in modern development, the larger a repository grows, the more we rely on these massive build systems to just, figure out what code affects what other code. We want them to hide the complexity.
Right, because nobody has the whole app in their head anymore.
Exactly. But in hiding the complexity, they start hiding the truth. A0 is designed to strip away those illusions. It takes those red checks, the failed linting rules, the broken type checks, the dependency policy violations, and instead of giving you a convenient way to sweep them under the rug, it exposes them as persistent visible state in the scheduler itself.
So it forces honesty. But how does it actually do that practically? Because according to our sources, A0 keeps the standard project.json and inc.json files as the workspace contract.
It does, yeah.
So it reads the exact same configuration files that NNX uses, but then it completely drops the NNX runtime. Why would you keep the blueprint but throw away the engine that was built for it?
Because the blueprint is actually sound, but the engine encourages bad habits. The project.json file is a really fantastic standardized way to describe the shape of a project. Its targets, its dependencies, its scripts, and NS recognizes that value.
So the data structure is good.
Right. But traditional runtimes often try to be everything to everyone. They run these heavy background processes. They try to emulate every possible edge case through massive plugin ecosystems. And, they just allow for an immense amount of fuzziness.
A lot of wiggle room.
Exactly. NS says we will accept the contract of what your project is, but we fundamentally reject how you currently execute it. So instead of routing tasks through a bloated plugin architecture, N routes the actual work through a highly restrictive math-based task runtime.
Which brings us to what the developers call workspace truth. The documentation states the entire goal of this tool is answering just a few basic questions, like what changed, what depends on it, what must run, and what failed.
Sounds simple enough, right?
Yeah, it does sound simple. But the source lists these hard wins that Aider achieves. And the one that immediately jumped out to me is that the commands quality, affected, run, and run many all share a single graph discipline.
That is a huge structural shift.
Right, but as a developer, you might assume they already do that in standard tools. Aren't they all just looking at the same code?
You would definitely assume that, but under the hood of many popular task runners, they really don't. Think about your standard workflow. You might run a command to test a single project.
Okay.
That command triggers a specific internal logic path. Then later, you run an affected command to test everything that changed since your last commit.
Right, to see the blast radius.
Exactly.
Right.
But that relies on a completely different script or plug-in logic to calculate the dependency graph. Because they are technically separate scripts, they inevitably drift out of sync. Have you ever, gotten a passing grade when you run a test locally, but then the continuous integration server runs the affected script and it just fails?
All the time. It is
Hmm.
infuriating. You spend hours trying to figure out why the CI server hates you when it works perfectly on your own machine.
Exactly. And that happens because the two commands are evaluating the dependency graph using different sets of rules. By forcing every single command to share one unified graph discipline, A eliminates that discrepancy entirely.
So the math doesn't change.
Right. The mathematical rules of what depends on what do not change based on which command you happen to type in the terminal.
Okay, so it's enforcing consistency. But the strictness goes way beyond just unifying commands.
Mhm.
The documentation details that dependency policy admission runs before any linting starts.
Yes.
Now, wait a minute. Linting is almost universally the first gate, right? You check the syntax, you make sure the semicolons are there, you check the formatting. Why on earth is A0 running dependency checks first?
It seems backward at first, but to see why this matters, look at what happens when we zoom out to the whole workspace. A dependency policy gate checks whether you are fundamentally allowed to import a certain package based on the architectural rules of the repository.
So like high-level architectural boundaries.
Right. Imagine you have a strict rule front-end UI components are never allowed to directly import back-end database drivers.
Oh, that would be a nightmare.
It would. If a developer makes that import, they have violated the structural integrity of the application. A0 looks at that and says, the structure is invalid. Why would I waste CPU cycles checking if your semicolons are in the right place when the entire architectural boundary is compromised?
It's like checking if the foundation of a house is cracked before you start arguing about what color to paint the living room. If the foundation is broken, the paint really doesn't matter.
Precisely. It is a profound shift in priorities, and it extends to how the tool discovers the projects themselves. A relies on an ignore file at the root of the repository, which supports ordered patterns and negations, but it explicitly, deliberately ignores the existing xignore file.
Even though it reads the x.json contract, that seems almost petty. Why ignore the existing ignore file?
It's a concept they call honest boundaries. If A0 were to read the xignore file, it would implicitly promise the developer that it respects and understands every single rule, quirk, and plugin assumption governed by a completely different runtime's philosophy.
Oh, it would be taking on all that technical debt.
Exactly. Adopting someone else's baggage. By forcing you to define exclusions strictly in a ignore, it draws a hard line. It ensures the rules of engagement are explicitly and transparently defined for the A0 scheduler alone.
I understand the philosophy, but I have to push back here. Strictly speaking, from a business perspective, this level of strictness can border on the absurd. Let's go back to our hotfix scenario from the intro.
The Friday night nightmare.
Yes, the site is down, the company's bleeding cash. A formal verification gate is failing because a developer didn't update some arbitrary architectural rule, but the actual code for the hotfix is sound. It'll bring the site back up. As an engineering manager, I don't care about a dependency policy in that exact second. I need the button to work. You're telling me A0 just blocks it.
It absolutely blocks it, and that is exactly the engineering culture A0 is designed to eradicate.
But the business is losing money.
And that mindset, fixing the button by ignoring the structural failure, is exactly how you introduce a regression that corrupts the database an hour later, costing the business 10 times as much.
So you're trading short-term uptime for long-term disaster.
Exactly. A0 forces you to realize that if your hotfix bypasses the established rules of the repository, you aren't actually fixing the system. You are just gambling. You're taking on unverified risk.
Which brings us back to that flag. The source states there is an --irresponsible flag to bypass these gates, and it literally maintains an alias for it, which is --you will be fired.
What's really fascinating here is the psychological weight of that design choice.
Yeah, it's not subtle.
Not at all. In traditional tools, developers use force flags like --force or skip checks as just casual conveniences. They are band-aids to make annoying red text go away. A0 turns those failed gates like linting, testing, formal proofs into persistent scheduler state.
So it remembers that you failed.
It remembers. It prevents the system from making an unsafe target safe simply by trying to run it again. When you type dash dash, you will be fired, you are actively creating a massive, glaring audit trail event. You are explicitly telling the scheduler, and by extension your entire team, I am intentionally violating the safety guarantees of this workspace, and I accept the consequences.
Wow. It's not a convenience toggle at all. It's a risk marker in the lab notebook. It's a confession.
Exactly. It exposes the reality of the technical debt you're introducing in real time.
Okay, so AZ is strict. It refuses to lie to you, it checks dependency policies before linting, it unifies the graph discipline, and it literally threatens your job if you try to force a bad build.
Very effectively, I might add.
But mechanically speaking, if the system is running these massive dependency checks, analyzing structural policies, and calculating perfect graphs before every single action, I mean, mathematically, that should take hours. Standard tools use heavy background daemons just to survive that kind of computational load. But you mentioned earlier AO throws the daemon out entirely. How is it physically possible to compute all of this without melting the developer's CPU?
And this is where we have to look under the hood at the engine room of Azure. The engineering here is remarkable. The execution model is fundamentally different from what you're used to. The documentation describes it as an atmospheric pressure cannon.
Okay, here's where it gets really interesting. Atmospheric pressure cannon. That sounds like a weapon. The source notes describe this as having minimal pressure, immediate release, no daemon ballast. Walk me through that. What exactly is daemon ballast?
So to keep things fast, most modern monorepo tools rely on a daemon. That's a background process that starts up when you turn on your computer and just sits there in your system's memory.
Just lurking in the background.
Yeah, right. It constantly watches your file system, holds the massive dependency graph in RAM, and tries to predict what you're going to do next. That is the ballast. Over a few hours of development, that daemon consumes gigabytes of memory. And worse, it often gets out of sync with what is actually on your hard drive.
Oh, absolutely. The classic, have you tried killing the daemon and restarting it? Troubleshooting step. Half my day is spent resetting the tool that's supposed to be saving me time.
Right, it's a known pain point. A&E strips that entire concept out. The atmospheric pressure cannon means that when you issue a command, ADO spins up from zero, calculates exactly what needs to be done with incredibly minimal overhead, that's minimal pressure, executes the tasks immediately, and then completely releases the resources.
So it fires the cannon and then resets.
Yes. It does not leave a heavy, stateful background process dragging your machine down.
But how? I mean, if it drops the state, how does it calculate the dependency graph so quickly from a cold start? The source text talks about a meta-laminar pipeline of laminar pipelines, where each ready frontier becomes a GG batch and folds into the next frontier.
It's dense terminology, I know.
It is. It also mentions speculative frontier planning. I know all those words individually, but together they sound like pure science fiction. What does laminar even mean in a software context?
So think of fluid dynamics. Turbulent flow is chaotic, right? Particles crash into each other. Laminar flow is smooth. Particles move in parallel, perfectly aligned lanes without interference.
Okay, I can picture that.
In A laminar pipeline means that data and tasks flow through the execution engine in perfectly parallel lanes without ever blocking each other or causing race conditions.
Okay, so tasks aren't crashing into each other. But how does it schedule them if there's no background watcher?
A graph of tasks has dependencies, right? Task B needs task A to finish first. A frontier is the set of tasks that have no pending dependencies. They are ready to run right this exact second. A takes that ready frontier and groups it into a batch.
Got it.
But here is the genius part. Speculative frontier planning. While that current batch is actively running on the CPU, A doesn't just sit idle waiting for it to finish. It speculatively compiles the next batch of tasks, assuming the current ones will succeed. It is constantly feeding the CPU in these smooth, laminar waves. It never stops to think. It thinks while it executes.
That makes a lot of sense. It's like a hyper-advanced assembly line where the factory is already speculatively building the parts for the next car based on what's happening right now.
That's a perfect analogy.
But to manage that, the source mentions some very dense algorithms. It cites Wallington rotation for low overhead lane assignment and permit reuse. Now, Wallington rotation sounds like a maneuver you'd pull in a fighter jet. What is a permit reuse, and why do I care about lane assignment?
Let's ground this in how your computer's memory actually works. When you run concurrent tasks, say compiling 50 different modules at once, your system only has a limited number of CPU cores and memory channels. We can call these execution lanes.
Okay, lanes on a highway.
Right. Usually a task runner creates a new thread, asks the operating system for permission to use a lane, runs the task, and then destroys the thread. That asking and destroying process takes a microscopic amount of time, but multiplied by 10,000 tasks, it creates massive lag.
Death by 1,000 cuts.
Exactly. Wallington rotation is an algorithm A0 uses to manage a permit pool. Think of it like toll booths on that highway. Instead of tearing down the toll booth and rebuilding it for every single car, A0 keeps the lanes open.
Oh, that's smart.
Yeah. As soon as one task finishes, the permit is instantly rotated to the next waiting task in the queue with near zero overhead. The execution thread never sits idle waiting for permission to proceed.
Okay, I'm tracking with the toll booths. But what happens when the traffic is literally driving in a circle? The source specifically points out Gnosis-style fork/fold semantics with SEC collapse. So cyclic workspace subgraphs do not deadlock. Let's break that down. A cyclic subgraph is a circular dependency, right?
Yes, exactly.
So package A needs package B to compile, but package B has an import that needs package A to compile. In every tool I've ever used, that just causes an infinite loop until the system crashes out of memory. How does A handle it?
This is one of the most elegant mathematical solutions in the entire project. SEC stands for Strongly Connected Component. In graph theory, an SEC is a cluster of nodes where you can draw a path from any one node to any other node. It's a cycle.
A loop?
Right. Standard task runners hit a cycle and freeze. They wait for A to finish so B can start, while B waits for A deadlock. A new uses SEC collapse. Before it even tries to run the code, it maps the graph, detects the cycle preemptively, and mathematically collapses those two dependent packages into a single unified execution node.
Wait, it just squashes them together?
It just squashes them. It tells the execution engine, I cannot run these sequentially without deadlocking, so I must treat them as a single, combined fold operation. It mathematically eliminates the possibility of the infinite loop before the CPU even receives the instruction.
That is brilliant. But A0 doesn't just stop at preventing infinite loops. The source says it runs Eon logic, structural, and fork/race/fold verification on every emitted GG batch before execution. It's not just scheduling the work. It's literally proving the work is safe to run.
And this is the core of that workspace truth philosophy. Aeon logic verification acts as a model checker. Before a single line of your code is executed, Azure looks at the speculative batch of tasks and checks for race conditions.
Like two things trying to save a file at the same time.
Exactly. If two tasks in parallel forks are trying to write to the same output directory, Aeon logic flags it as a structural failure. Every single batch is mathematically verified to be sound before it touches your CPU. It guarantees that the build system itself will never introduce a random intermittent fault into your pipeline.
That level of mathematical rigor is just staggering. But again, if it's doing this constantly without a daemon, we have to talk about caching. Because doing deep math on thousands of files takes time. The README highlights two distinct types of caching to speed this up: corridor caching and sticky pass caching. What is the difference there?
So corridor caching is macro level. Let's say you have a massive library. I/O takes a cryptographic fingerprint of that entire project, plus the fold of its dependencies.
A folding meaning?
Meaning the exact state of everything it relies on all the way down the tree. It caches the result of that entire corridor of execution. If you run the build again and the fingerprint matches perfectly, AO skips the whole thing. It is instantaneous.
Nice. And sticky pass caching. The source says this is for parsable ESLint targets, plus preserved sticky isolated test execution.
That is micro level. Imagine an ESLint target that covers 5,000 individual files. If you change just one typo in one file, corridor caching would invalidate the entire project.
And you'd have to relint all 5,000 files. That's so slow.
Exactly. Sticky pass caching remembers the exact pass-fail state of each individual file within that target. So if you change one file, A0 only relints that one specific file, relying on the sticky cache for the other 4,999, but it magically does so while maintaining the integrity of the overall task graph.
That's incredibly efficient. And to make sure those caches are ready, it has an eager warm mode. The documentation says it watches workspace edits and replays selected graphs to keep hot caches resident. So even though it threw away the heavy daemon, it's still lightly watching your files to prep the cache for when you finally hit enter.
Yes, but the critical difference is how it watches. A standard daemon tries to hold the entire world in memory and react to every single keystroke. A0's eager warm mode is highly targeted. It watches for bursts of edits, folds them together, and selectively updates the cache for only the specific topological paths you're actively touching.
It's surgical.
Highly surgical cache warming.
Okay, so internally, for our own code, this engine is a marvel. It collapses cycles, it verifies paths, it manages memory with Wallington permits. But modern development doesn't exist in a pristine, isolated vacuum. We rely on external code. We pull down open source libraries. We use massive package registries. We build Docker containers. How does A0's hyper-strict verification handle the absolute wild west of NPM dependencies? Because let's face it, the public NPM registry is a mess of conflicting versions.
Oh, it's chaotic.
Which brings us to how A0 handles strict installs and topology compilation.
This is perhaps where A0 makes its most controversial yet structurally necessary decision. The documentation plainly states that A0 install completely replaces package managers like npm, pnpm, yarn, or bun.
No, hold on. You can't just throw out NPM. Billions of packages rely on those specific resolution algorithms. Developers have spent years optimizing their PNPM lock files. If I drop A0 into an enterprise repo today and just rip out the package manager, isn't it just going to break instantly? I mean, 90% of open source packages have deeply messy, broken dependency trees.
It absolutely will break instantly.
Right.
And A0 considers that a feature, not a bug.
A feature. Telling a developer they can't install a popular library is a feature.
Well, traditional package managers have escape hatches built in because they prioritize getting you to a working state, even if that state is fundamentally flawed. Azure refuses to compromise on workspace truth. When you run a zero install, it doesn't just blindly download files from a registry. It compiles your entire workspace dependency graph into a topology. And then it runs it through what the documentation calls Betty's 13-phase compiler.
A 13-phase compiler just to install a JavaScript package. What is it even doing? I type install React, it downloads React. What are the other 12 phases?
It's doing deep graph analysis. Phase 1 might be parsing the package.json, but subsequent phases involve integrity hashing, topological sorting, cross-referencing peer dependencies across the entire monorepo, and looking for impossible version constraints.
It's analyzing everything.
The compiler is looking at the entire ecosystem of your code at once. And one of the most intense phases is finding circular dependencies using Tarjan-style DFS.
Okay, let's ground that. For a developer who hasn't taken a computer science graph theory class in 10 years, what is Tarjan's algorithm actually doing differently than just reading a list of packages from top to bottom?
So DFS stands for depth-first search. Imagine you're in a maze, and you keep your right hand on the wall and walk as deep into the maze as you can until you hit a dead end. Then you back up and try the next path.
Okay, pretty standard way to solve a maze.
Right. Tarjan's algorithm does this through your dependency tree. Package A needs B, B needs C, C needs D. It goes all the way to the bottom. But while it does this, it leaves breadcrumbs. If it's walking down the tree and suddenly encounters a breadcrumb, it already dropped, meaning C actually requires A. It instantly flags a back edge.
Ah, so it found a cycle.
Yes. It has mathematically proven a cycle exists without having to guess or wait for a timeout.
And once it maps all of this, the source says it enforces Boolean positivity. I love the sound of that phrase. But what does it mean in practice?
Boolean positivity is a strict rule. Every single package in your entire workspace must have at least one valid, resolvable version that completely satisfies all constraints without conflicting with anything else.
Meaning, no two packages can demand incompatible versions of a third package.
Exactly. If package X needs version 1 of a library and package Y needs version 2, and they cannot be reconciled natively, the installation just fails.
This is exactly why those force flags exist. The documentation explicitly says, if the topology fails verification, installation is refused, strictly and without compromise. No -- force, no -- legacy peer deps, no -- shamefully hoist. If I'm using NPM and I hit that version conflict, I just type -- legacy peer deps and it forces it to install anyway.
And this raises an important question. Why do we accept tools that let us force broken code into our projects?
Because we have deadlines.
Sure, but the force flag tells the package manager, I know the math doesn't work, just pick a version and hope it doesn't crash at runtime. Ainier's philosophy is that hoping is not an engineering strategy.
That is a harsh truth.
If the graph cannot be mathematically resolved by the Boolean positivity check, you cannot install it. You are forced to actually fix your dependency tree, update your libraries, or fork the offending package. Aider locks the door and throws away the key.
It is brutal, but I see the logic. It's preventing the exact kind of runtime errors that take down production servers at 3 a.m. So how does it actually fetch the packages once it finally agrees the math is sound? It says package.json is still the lingua franca, so it's not inventing a new format.
No, it uses standard formats. It uses Node22's built-in fetch command to talk directly to the NPM registry, caching the metadata locally.
Huh.
And it uses that Wallington permit pool we talked about earlier to control the concurrency.
Oh, the toll booths again.
Right. It prevents your system from being overwhelmed by trying to open 10,000 network connections simultaneously to download tiny NPM modules. It parses, verifies, and downloads in highly controlled laminar parallel lanes.
And AZA doesn't stop its strictness at package managers. It applies this exact same iron-fisted graph logic to infrastructure. The source outlines a Docker, which auto-detects Docker files across your workspace and parses them into topologies.
This is a brilliant application of graph theory. Most tools treat a Docker file as just a dumb text script. From Ubuntu, Ronin, apt-get update, copy.to /app, exoppose 8080, they run it line by line and just hope it works.
Yeah, that's how I've always used it.
Ada translates those text instructions into a mathematical graph.
The source breaks down the mapping perfectly. It says from maps to fork nodes, run maps to process edges, copy -- from maps to race edges, and expose maps to vent nodes.
Think about the power of that translation. By mapping a Docker file to forks, processes, races, and vents, ASIC can pass your infrastructure through the Betty compiler and the Eon logic verifier before it ever talks to the Docker engine.
Oh, wow. So before it even pulls the images.
Exactly. If you have a multi-stage build where a copy y -- from references a container stage that hasn't been built yet, creating an impossible race condition, standard Docker will just start building, make you wait 20 minutes while it downloads Ubuntu, and then crash on step 18.
I've been there. It is soul-crushing.
ASIA's structural verification catches the race condition instantly as a diagnostic error and refuses to even begin the build.
That alone would save hours of developer time. It proves the Docker file is mathematically valid before the build even starts.
Exactly. It turns infrastructure as code into infrastructure as mathematics.
Okay, so let's take a breath and look at where we are. We have a system with an atmospheric pressure cannon engine that collapses cycles, verifies internal tasks, strictly refuses broken NPM installs, and mathematically proves Docker files.
It's a lot.
It is a lot. And because of all this strict verification, A0 is generating an absolutely massive amount of telemetry and status data. Every permit, every cache hit, every Boolean positivity check. How is all this data tracked and managed, especially since we made such a big deal earlier about throwing out the background daemon? This brings us to the nervous system of AZA, the control plane, QDoc, and telemetry.
Yes, this is where A0 evolves from a really fast task runner into a distributed control system. AZE uses a local first control plane that emits what the documentation calls OTel-shaped task spans.
OTel meaning open telemetry.
Yes, open telemetry is the industry standard for observing how complex software performs. But A0 doesn't just fire these telemetry spans off into the void or send them to a third-party cloud service. It mirrors them into a local JSON-al audit trail and maintains a canonical QDoc workspace mesh.
Let's unpack QDoc workspace mesh. A mesh usually implies a network of connected nodes. The source says this mesh tracks runs, tasks, deployments, formal receipts, logs, VFS virtual file system snapshots, and leases. It sounds like a decentralized ledger for everything happening in the monorepo.
That is a perfect way to conceptualize it. Because there is no central daemon holding the state of the workspace in volatile RAM, the state has to be persisted somewhere. It is persisted in this QDoc mesh. It acts as the single immutable source of truth, the canonical control document.
And developers interact with this mesh using specific commands. The README lists a zero control serve and a zero control worker. Let's look at serve first. The source notes say it keeps the workspace control QDoc hot locally, syncs it over -relay when available, continuously ingests forge router log, aggregate metric, and control event streams into the same mesh. So serve is essentially the anchor.
Yes, serve maintains the live state of the QDoc. And when it mentions -relay, it means this control plane isn't trapped on your local laptop. -relay is the transport layer that allows the workspace mesh to synchronize across a network of machines. It ingests all this telemetry and serializes the data so multiple machines don't overwrite each other.
Which perfectly sets up the A0 control worker command. The source highlights some really interesting flags here, like -- parallel equals 2, -- accept equals remote auto. It says the worker claims runnable tasks from the workspace mesh, heartbeats leases, executes them, writes task and log state back into the same control doc. Walk me through the mechanics of a lease and a heartbeat.
This is classic distributed systems architecture applied to your local build tool. A task is generated, say, compiling a front-end app and placed into the QDoc mesh. A worker node sees the task, claims a lease on it, meaning it calls dibs, and starts compiling.
Okay, it claims it so no one else does it.
Right, and as it compiles, it continually sends a heartbeat signal back to the QDoc mesh saying, I am still alive, I am still actively working on this task.
But what if the worker's internet connection drops? Or its CPU kernel panics?
The source specifically addresses this. It mentions stale worker detection once the heartbeat goes quiet. If that ping stops arriving, the serve command notices. It automatically detects the worker as stale, invalidates the lease, reclaims the task, and puts it right back into the mesh for a different, healthy worker to claim.
Oh, that's so resilient.
It provides absolute fault tolerance without needing a monolithic memory-hogging demon. The state lives safely in the mesh, not in the fragile memory of a single worker process.
And it monitors the network itself to prevent that. The documentation points out that the serve command tracks reconnect, drop, error counters, and flapping alerts over the dash relay transport.
It has to. If your entire build system relies on a distributed mesh to agree on the workspace truth, the health of the network transmitting that truth is just as critical as the code itself.
So as a developer, if I am sitting at my terminal, how do I actually see this mesh? All this telemetry sounds great for a machine, but what am I looking at? The documentation lists a command called a zero-top, and it has flags like --watch, --intervals equals 2000. The source says it renders the control snapshot as a watchable operator view for humans, including live mesh task and run pressure, worker session state, relay transport health, and hot fault summaries.
It's a dashboard.
Yeah, to me this sounds exactly like opening up the activity monitor on a Mac or the task manager on Windows. But instead of just seeing CPU usage, you are seeing the literal heartbeat and health of your entire development team's tasks mapped across the network.
That is exactly what it is.
Yeah.
A zero-top is the activity monitor for your monorepo. And the beauty of it is that because it reads directly from the canonical QDoc mesh, there is zero ambiguity. You are looking at the exact same data the scheduler is looking at. You see every worker, you see their relay status, you see the exact millisecond a heartbeat goes quiet.
It also mentions Azure control for repo-wide status and Aether logs. You can run Aether logs with project or workspace. The source explicitly notes that it reads normalized process logs from the control doc, the local forge router, or the remote forgo log adapter. So Aether changes the nature of logging too.
Think about standard terminal logs. They are ephemeral text streams, right? They scroll past your face, and when you close the terminal window, they are gone forever.
Lost to the void.
Exactly. By piping the logs through the QDoc mesh, Aether normalizes them. They are normalized, structured data appended to the immutable history of the workspace. If a build failed 3 days ago on a remote worker, the exact log of that failure is still queryable in the mesh.
It's an incredibly robust nervous system.
Yeah.
But we've reached an interesting point. We've built this ultimate, mathematically verified, perfectly tracked workspace. We've proven the dependencies with Tarjan's DFS. We've squashed the cyclic graphs. We have telemetry flowing perfectly over dash relay.
Everything is perfectly in order.
Right. Now, how does A0 take this pristine code and push it out into the messy, real world? And perhaps more importantly, how does that help a team manage the inevitable technical debt that accrues over years of development? That brings us to our final exploration. The edge, covering formal verification, Cloudflare deployments, and natural language queries.
This is where we see the ultimate payoff of all the strictness we discussed in the first half. Because A0 enforces absolute, uncompromising truth at the base foundational level, its higher-level features can operate with a level of trust and automation that is simply impossible in traditional tool chains. Let's start with the formal verification aspect.
The source mentions failed closed formal verification for Lean and TLA. Now, TLA Plus is a formal specification language used by engineers at places like Amazon to design complex distributed systems. And Lean is a mathematical proof assistant. Are you telling me Aether is integrating literal mathematical proofs directly into the standard build pipeline?
Yes. It provides a lightweight check for local pre-commit use, but an authoritative Lake build verification on strict and deploy paths. Lake is the package manager for Lean. What this means is that before you are allowed to deploy your code to production, A0 enforces that your formal mathematical proofs, the logic that proves your algorithms are mathematically flawless, actually compile and pass.
And when they do?
A0 generates what the source calls exact match formal receipts.
A cryptographic receipt for math. It literally gives you a receipt proving the logic holds up before the deploy gate opens.
And it manages the immense computational weight of this elegantly. The source details manage cache stewardship for .lake and .cache directories, including dependency build pruning, mathlib cache hydration, and low disk eviction.
Mathlib is huge, isn't it?
It's massive. Running mathematical proofs requires these massive libraries. A0 automatically hydrates those caches when needed and evicts them when your hard drive gets full, so the developer never has to manually manage the overhead of formal verification.
That takes so much friction away. And once you have that verified receipt, you move to deployment. The documentation outlines AZ Forge deploy and specifically calls out Cloudflare worker execution. It says it materializes a temporary Wrangler config from admitted eon/forge runtime NV, so project graph deploy targets keep their depends on semantics without app local wrappers. Let's translate that. Usually to deploy a Cloudflare worker, you need a configuration file called wrangler.tomuret sitting in your specific app directory.
Right. And if you have a massive monorepo with 100 different Cloudflare workers, you suddenly have 100 different wrangler.tomu files scattered everywhere.
Yes.
Ensuring they all share the right environment variables and respect the repository's dependency graph becomes a maintenance nightmare. They constantly drift out of sync.
So AS solves this dynamically. It reads the centralized runtime environment from the control plane, and at the exact millisecond of deployment, it materializes a temporary Wrangle config out of thin air.
Out of thin air.
It injects the depends on graph semantics, uses the config to execute the deployment perfectly, and then it's just gone. You don't have to clutter your repository with local wrapper scripts.
It is a pure application of the single source of truth. The workspace QDoc mesh already knows exactly what the deployment needs, so it just generates it at the edge.
It's beautiful. And speaking of keeping the repository clean, let's look at the and0 clean artifacts command. The flags are --scope equals root or workspace and --dry run. The source states it prunes only known generated artifact directories and refuses to touch any candidate that still contains tracked files.
This specific feature is a direct response to a very common, very painful developer trauma.
I think I know where you're going with this.
Think about how many times you've run a clean command like git clean -fdx or a custom npm clean script, only to realize a split second too late that you were in the wrong directory. Or you had uncommitted source code sitting in an output folder, and the script just blindly nuked a week's worth of work.
I physically flinched when you said git clean -ftx. Yes, it happens to everyone.
Azer's clean command is structurally aware. It doesn't just run a dumb regex pattern to delete folders. Before it deletes anything, it checks the version control system. It asks, does this specific directory, which I'm about to obliterate, contain any files that are tracked by Git?
And if it does?
If the answer is yes, it absolutely refuses to touch it. It protects the developer from their own mistakes.
It's completely idiot-proof. But the last two commands we need to cover are where we cross from strict engineering into almost sci-fi territory. First is A0 ask. You type A0 ask, a question in quotes, and you can add an intent flag. It dispatches natural language queries against the workspace control doc to answer questions about health, costs, ownership, and blast radius.
This raises an important question about how we fundamentally interact with giant code bases.
Right.
Traditionally, finding the blast radius of a change meaning, if I modify this authentication module, what other 50 projects might break? Requires running complex grep commands across the terminal, visualizing messy graphs, or just relying on the tribal knowledge of the senior engineer who built it 5 years ago.
Who might be on vacation.
Exactly. AA0 changes the paradigm. Because the workspace is a perfectly tracked, formally verified database, that QDoc mesh we discussed earlier, developers can literally ask the system in plain English, what is the blast radius if I change this file?
And what's crucial here is that because AO enforces truth at the base level, because it knows the exact topology from the Betty compiler, the SEC collapses, the Boolean positivity, the answer it gives you isn't some AI hallucinating a best guess.
Yes.
It is a deterministic, mathematically verifiable answer based on graph truth.
Yes.
The natural language is just a convenient UI on top of absolute certainty.
Precisely. It turns the entire history and structure of the monorepo into a queryable database.
Yeah. And that leads us to the final command, which might be my favorite concept in the entire document. A zero vacuum. You type zero vacuum, your intent, and then -- target state equals your expected resolution. The documentation describes this as instantiating an attractor for a topological debt. It bypasses a traditional REPL loop by siphoning background daemon telemetry until the target state is reached and the vacuum collapses. Okay, an attractor for a topological debt. That sounds incredibly poetic, but what does it actually do?
Let's build a scenario. Imagine you have a massive 5-year-old code base. Deep in the architecture, there is a deprecated logging library that is causing memory leaks, and it is imported in 400 different files. You want to eradicate it.
A noble goal.
Right. In a normal company, you create a Jira ticket, you have sprint planning meetings, and you hope that over the next 6 months, developers remember to slowly swap it out. It is a manual, agonizing process of tracking technical debt.
Yes, the classic "we'll fix it in Q3" promise that never happens.
The 8 as 0 vacuum command automates the monitoring of that promise. You create a mathematical attractor in the workspace state. You define your intent, eradicate the logging library, and you define the expected resolution 0 imports of that library remaining in the dependency graph.
So it's like setting a smart thermostat for your technical debt. You set the target temperature, and the system just invisibly monitors the environment.
Exactly. You don't have to write a custom script or enter a read evil print loop every week to check the status. The vacuum sits quietly in the QDoc mesh. It siphons the telemetry flowing through the control plane day after day. It watches the test results, the dependency resolutions, the commits. As your team naturally evolves the codebase over 6 months, slowly removing the library file by file, the vacuum measures the topological debt shrinking.
And
The moment the final import is removed, the vacuum detects that the target state has been reached, confirms the debt is resolved, and automatically collapses. It tracks the eradication of technical debt with 0 meetings and absolute mathematical precision.
it is a stunning piece of engineering. Let's zoom out and recap the journey we've been on with A0. We started with a fundamental philosophical shift: the pursuit of absolute workspace truth. We saw how it forces honest boundaries by making red checks visible, persistent state, and how it literally gives you a -- you will be fired flag if you try to gamble with unverified hotfixes.
And we then explored the engine making this rigor physically possible. The atmospheric pressure cannon that drops heavy Daemon Ram ballast. We saw how it uses Lambda pipelines, speculative frontier planning, Wallington permit pools for memory efficiency, and SEC collapse to preemptively squash deadlocks, all while running Aeon logic verification on every single batch before execution.
We looked at the iron gates of A0 install, where it fundamentally rejects the messy compromises of standard package managers. We walked through how the 13-phase Betty compiler uses Tarjan's DFS to find back edges, enforces Boolean positivity, and completely maps Docker files into verifiable graph topologies so they fail fast before they even build.
From there, we examine the nervous system. The local first control plane generating hotel-shaped spans into a decentralized QDoc workspace mesh. We unpack the mechanics of workers claiming leases, sending heartbeats over Dash Relay, and how tools like a Zerotop act as a pristine activity monitor for the entire distributed network.
And finally, we arrived at the edge, where this strict foundation allows for literal mathematical proofs to generate formal deploy receipts. We saw dynamically materialized Cloudflare Wrangler configs, artifact cleaning that refuses to touch tracked source code, and the sci-fi reality of asking a monorepo natural language questions to track an automated vacuum pulling your technical debt towards 0.
A0 ultimately forces us to rethink our entire relationship with our code. For years, we have been conditioned to coerce our tools to just make it work. We bypass errors, we ignore deprecation warnings, we slap on -- force flags, and we restart crash daemons just to get through the workday.
Because it's easier.
Exactly. But if a system like A0 perfectly tracks every failure, mathematically enforces every dependency topology, and verifies every deployment against formal proofs, it begs a profound question. If the scheduler absolutely refuses to let us lie to ourselves about the health of our project, do we eventually reach a point where the workspace scheduler understands the structural integrity of the software far better than the human developers who wrote it?
That is a wild thought to leave on. The X-ray machine isn't just taking the picture anymore. It's physically locking the hospital doors and refusing to let you leave until it mathematically proves the bone has healed. Thank you so much for joining us on this deep dive. Take a look at your own repositories today. Think about the tools you use and ask yourself just how much actual workspace truth exists in your codebase right now.